Hello, so we've learnt about the benefits of using a factorial design to set up our experimental groups when we are asking difference questions. Now what we're going to do is we're going to consider how we can use our experimental design to minimise the effect of confounding variables that might pop up and reduce our statistical power unintentionally. So what we're going to do is to go through 3 different problems that might arise with our experiment, and we're going to consider how we can design our experiment so as to minimise those problems. And we're also going to go through potential statistical fudges that we can use to rescue an experiment that may not have properly considered how to minimise these problems. So the first problem is the unintended effects of manipulation, things that might arise because of all the things that you do to bring about your manipulation. I mean, like, if you're performing a surgery, like the procedure of going under the anaesthetic, for example, might affect the variable you want to measure, something which isn't the manipulation that you're trying to observe, but is something which you have to do in order to conduct that manipulation. And the solution of this, for this, of course, is to include the appropriate control if it's necessary. Now, there's no statistical fudge if you didn't include the appropriate control. The Bible of using R, the R book by Mick Crawley, contains a whole chapter on controls, and the entire chapter just reads no controls, no conclusions. I maybe wouldn't be quite as drastic as that because not every experiment needs a control, but we're going to consider controls slightly later in the next video. The next thing is common confounds, your response variable is often affected by things like the body size of your subject animals or the age of your animals, etc. And the solution to this, in terms of experimental design, is to use either something called pairing or something called blocking, which is to choose groups of animals which share similar values for the characteristics that might be common confounds. So, for example, you find a group of animals which are all of the same age, and you perform your experiment on those. We'll go into pairing and blocking in a later video, but the statistical fudge that you can use to help rescue an experiment if you didn't adequately pair or block your experiment is something called analysis of covariance, or ANCOVA. Now, you might have heard of this. I think you've probably learnt this already with in your R lessons with Leslie. So that is where you as predictor variables in an analysis, you have both your treatment groups that you want to measure differences in, but also you fit the potential confound, like age or body size, as a covariate. And of course you have already to have measured that covariate if you want to include it in your analysis. So of course you need to have measured it, but if you've done that, then often you can use an ANCOVA to statistically remove the effect of the confound and then look at the effect of your treatment group while accounting for the effect of your covariate. So ANCOVA is a potential statistical fudge if you have measured your potential confound. A slightly more problematic thing is unknown confounds, so shared variables that you haven't measured. So if you haven't measured body size or age or something, but you suspect that some of your experimental subjects might share values of age or body size that might be potentially driving some of the patterns that you're using, then you need to try to account for that in your experimental design. And the solution is to randomize, is to make absolutely sure that you have tried as hard as you can to randomize the allocation of individuals to each of your treatment groups. So you need to make sure that you've instead of choosing the first 10 animals that you find and allocating them to treatment A, and the last 10 animals that you find and allocating them to treatment B, you need instead to as far as you possibly can to randomize the allocation of of animals to different treatments, and that will go as far as possible to eliminating or reducing the effect of unknown shared unmeasured variables. Now this is the cause of what we call pseudo-replication. It's really kind of where subjects in your experiment share values of variables that you can't anticipate. So it's like they are likely to share lots and lots of features of maybe their genetics or maybe their environment, which are likely to drive patterns that you want to measure, but you need to remove, you need to account as far as possible for the effect of shared unmeasured variables. So one way is to randomize. Another way is to remove or to reduce the effect of pseudo-replication is know what the true unit of analysis is, and ensure that the experiment is well replicated at that level. So remember, I was talking about, if you measured 5 individuals from the same family and 5 individuals from another family, you can't then say you have 10 independent replicates. In fact, you've only really measured 2 families, and the 2 families are likely to share lots of things to do with their genetics and environment, which mean that they're likely to share values. So your real unit of replication there is the family, and so when you think about your sample size, you should really be trying to get as many families as possible in that particular case. But it doesn't have to be family that's your unit of replication. It could be, treatment block. It could be, the number of villages you do your analysis on. Anything where individuals might share values, share features of their genetics or environment, which could drive patterns that you see in your response variable. Now there are more complex statistical ways to account for this, something called multi-level modelling or mixed effect modelling, but that's something which you won't meet during your undergrad, and we are happy to help people do that during things like your final year project, for example, but it's something which we won't go over in detail here or during your undergrad. It's something which is taught at master's level. So what we're going to do now in the next couple of videos is to go through in detail some of the ways which you can use your experimental design to minimize confounding variables, talking about controls, talking about pairing and blocking, talking about randomization. So I will see you in the next video.